Concept of coding. When numbers, letters, or text characters are represented by a specific group of symbols, it is said that the number, letter, or text word is being encoded. So when the number, letter, or text characters they are represented by a specific group of symbols, it is said that the number, letter, or text character is being encoded. And the group of symbols is nothing but a code. The digital data is represented, stored, and transmitted as a group of binary bits. Such a group of binary bits is also called as a binary code. The binary codes can be used for representing the numbers as well as they can be used for representing the alphanumeric letters. So what are the advantages of binary codes? Binary codes are suitable for computer application, that is zeros and ones. The message can be transferred in the form of 0 and 1. The analysis and the designing of digital circuits becomes easy if we use the binary codes. As only 0 and 1 are being used, implementation of binary code becomes easy. Application of the binary codes is in two things: in digital communication and in computers. In digital computers. Classification of codes. The codes are classified into the following categories: weighted code, non-weighted code, reflective code, sequential code, alphanumeric code, and error detecting and correcting code. So one by one, what are the codes? Codes are weight codes, non-weight codes, reflective codes, sequential codes, alphanumeric and error detecting and correcting codes. So first is what? Weight codes. So explain in brief the weight and non-weight codes with one example. Weight codes are those codes which are based on the principle of positional weight. Each position represents a specific weight. Each position, each digit will represent a specific weight. Several systems are used to express the decimal digits 0 through 9. These codes have been listed up. The codes 8421, 2421, 3321 are all weighted codes. In these codes, each decimal digit is represented by a group of 4 bits. So these 4 bits are what? 8, 4, 2, 1. They are represented as a 4-bit number 8, 4, 2, 1. Non-weight codes. The codes in which weights are not assigned are called as the non-weight codes. So the codes in which you do not have positional weight, there is no positional weight are called as the non-weight codes. The examples are XS3 and Gray 3. So Gray codes and XS3 are the examples of non-weight. Gray code and XS3. Reflective codes. A code is said to be reflective when the 9th complement of the code for 0, code for 8 is the code for 1, 7 for 2, 6 for 3 and 5 for 4. So code for 9 is a complement of code for 0. Code for 8 is a complement for code 1, 7 for 2, 6 for 3, 5 for 4. Reflectivity is desirable in a code when the 9th complement is required to be found. Examples: 9 complement is nothing but the BCD subtraction. So 2, 4, 2, 1, 5, 2, 1, 1 and XS3 are examples of reflective codes. Sequential codes. A code is said to be sequential with each succeeding code word in one binary number greater than the preceding code word. For example, 0000, then 0001, 0010. So this is 4 zeros. Then you have one binary number greater, that is 0001. Then you have 0010, that is one more binary number greater. So the preceding code is one binary number greater than the succeeding code is one binary number greater than the preceding code. This greatly simplifies the mathematical operation to be carried out on the coder. The 8421 and XS3 are sequential codes, alphanumeric codes. The special code designed to represent numbers as well as alphabetical characters are known as alphanumeric codes. Some of these codes are capable to representing some symbols and instructions as well, in addition to the numbers and alphabet characters. Examples of alphanumeric codes are ASCII code, that is American Standard Code for Information Interchange, EBCDIC, Extended Binary Coded Decimal Interchange Code, and Holothrian code. Error detecting and correcting codes. When digital data or information is transmitted from one system to another, an unwanted electrical disturbance called noise gets added. So when the data is getting transmitted from one computer to another, there is certain unwanted message which is also transmitted in form of noise. The noise can force an error in the digital information. This means 0 may change to 1 or 1 can change to 0. So because of this unwanted noise, 0 can change to 1 and 1 can change to 0. To detect and correct such errors, we can use special codes which possess the capacity to detect and correct the error. Such codes are called as error detecting and error correcting codes. Parity can be used for error detection, whereas humming codes can be used for error correction. So for error detection, to detect the error, we use the parity checker, whereas for error correction, we use the Hamming code. BCD, Binary Coded Decimal Code. BCD is a short form for Binary Coded Decimal. In this code, each decimal digit is represented by a 4-bit binary number. Thus, BCD is a way to express each of the decimal digits with a binary code. The positional weights associated to the binary bits in the BCD are 8421, where 1 corresponds to the least, so LSB, and 8 corresponds to the most significant bit, that is the MSB. These weights are actually 2 raised to 3, 2 raised to 2, 2 raised to 1, 2 raised to 0, which are same as those of the normal binary system. So conversion of BCD, the decimal system 0 to 9 are converted into BCD in the same way as that of binary. So decimal 1 will be 0001. This will only be the BCD 1 also. So decimal and BCD 1 is same. Decimal and BCD 2 is also same. Decimal and BCD 3 is same. Decimal and BCD 4 is same. 5 is same. 6 is same. 7 is same. 8 is same. And 9 is same. So till 9 they are exactly the same. Now after 9 what happens? They change. For decimal number 4 corresponds to 0100 BCD, which is exactly the same as binary. Similarly, the BCD number corresponding to 0 and 9 are given in the table. Invalid BCD codes. With 4 bits, we represent 16 numbers, but in the BCD only we can represent the first 10 numbers. So 4 bits allows us to represent how many numbers? 16 numbers. But BCD allows us to represent how many numbers? Only 10 numbers can be represented. The remaining 6 code combinations, that is 1010 to 111, that is 4 times 1, are invalid in BCD. So from 10 onwards, binary equivalents become invalid. From 10 onwards, binary equivalents become invalid. For BCD. Conversion of big decimal numbers to BCD. To express any decimal number in BCD, simply express each decimal digit with its equivalent 4-bit code as illustrated. So for example, 98. So 98, binary for 9 is 1001. Binary for 8 is 1000. So this is the BCD for 98. Similarly, 164. If you want to represent 164, 1 binary is 0001, 6 binary is 0110, 4 is 0100. So this will be the BCD equivalent. So just simply each digit you have to represent as the binary equivalent and not the whole digit. The number, each digit should be represented as the equivalent. Smallest and largest number in the BCD. The smallest digit in BCD is 0000, that is 0, and the largest is 9. The next number is expressed will be 10 to the power 10, which will be expressed as 1 will be 0001 and 10. That 0 will be 000. So 10, how will you express in BCD? Binary for 1 is 0001. Binary for 0 is 0000. So 10 will be represented like this. Till 9, the BCD and the binary will be same. But from 10 onwards, the BCD will be this. So this is the BCD. And how will be the binary? 10, 2 5s are 0, 2 2s are 4, then 1, 2 1s are 2, 0, 2 zeros are 0, 1. So 1 0 1 0 will be the binary for 10, but the BCD for 10 will be 0001 0000. Comparison with the binary. BCD is less effective than the binary. Conversion of decimal number 78 into BCD and binary. So the number 78 will take 7 bits when you express it as binary number, and it will take 8 bits when expressed as BCD. So it is less efficient because it needs more bits. BCD arithmetic is more complicated than the binary arithmetic. The advantage of BCD code is that the conversion from decimal to BCD or vice versa is simpler. So these are the BCD codes. After 10, BCD and binaries are different. Before 10, BCD and binaries are same. So this is a very important table. Before 10, they are same. After 10, they are different. Even 10 is different. Packed BCDs. The BCD numbers corresponding to the decimal number beyond 9 are called as packed BCDs. So after 9, whatever numbers are represented in the BCD, they are said to be packed BCD. Packed BCD. Some examples of packed BCD are represented. So we have 25, 169, 1, 6, and this is 9. Binary for 5, binary for 2, and binary for 3. Advantages of BCD code. It is very similar to the decimal system. We need to remember the binary equivalence of only 0 to 9. No need to remember the other equivalents. We can automatically generate the BCD code. This advantage, the addition and subtraction of BCD have different rules. BCD arithmetic is a little bit of complication. BCD needs more number of bits than binary, so it is less efficient. So we saw that 78 in the binary system, it needed only 7 bits. In the BCD, it needed 8 bits. So the disadvantage is that disadvantage of BCD is that it is less efficient than the binary. Okay, convert the following numbers, decimal numbers, to the BCD. So 35. Binary for 3 is 0011. Binary for 5 is 0101. So this is the BCD for 35. For 174, 1 is 0001, 7 is 0111, 4 is 0100. For 2, 4, 7, 9. For 2 it is 0, 0, 1, 0. For 4 it is 0, 1, 0, 0, 0, 1, 1, 1. And for 9 it is 1, 0, 0, 1. So for binary equivalence, the shortcut is what? 8, 4, 2, 1. 8, 4, 2, 1. 1. If I want for 8, then I will write 1 against 8 and 0. For 4 it is 0, 1, 0, 0. For 2 it is 0, 0, 1, 0. For 1 it is 0, 0, 0, 1. For 3 it will be 1 plus 2 is 3. So for 3 it will be 0, 0, 1, 1. This way we can find for 0 to 9.